Okay, welcome back. So this is the first property that we have just discussed. So moving along, we have another property of frequency shifting. Again, it's a kind of a dual thing. Uh, it is we have already done that. If we have a signal x of t and it has a Fourier transform, say x of omega, j omega, whatever they not how this is description is. And if we model it, so it was something like this. If we shift this in time domain, say by some amount t minus t naught, then under Fourier transform in the frequency domain, it actually is we will be modulating by a factor j omega naught t, like this. Fine, this was the time shifting property. But we also have a dual of it, in the sense that if I multiply by e raised power j omega naught t in the time domain, then take the Fourier transform, it will be actually shifting in the frequency domain, something like this. Fine. So this was the original one, and this is it is, you can say it's dual. Fine. So earlier we used it to shift in time domain, which was equivalent in frequency domain, that you are multiplying your जो आपका transform है by the factor e raised power j omega naught t. Equivalently, if we multiply by the same factor in the time domain, then take the Fourier transform, it will be equivalent to shifting operation in the frequency domain. Again, you can easily prove it. I will just quickly go through the proof. So you have the original transform like this: minus infinity to plus infinity x of t e raised power minus j omega t d of t. So if I define the transform of this thing, so in other words, if I define, say, x tilde j omega as a transform of this signal e raised power j omega naught t x of t, then you have your own e raised power minus j omega t d of t. So if you do minus infinity to plus infinity x of t e raised power minus j omega minus omega naught t, combining these two exponentials, again this is equivalent to the Fourier transform of this argument. So it will be x j omega minus omega naught. Fine. So this proves this thing. But again, it's a kind of a dual. Like in the previous case, multiplication in time domain equals to convolution in frequency domain, as convolution in time domain equals to multiplication in frequency domain. So similar kind of logic can be applied here. It's a kind of a dual. So if you have shifting in time domain, it equals to multiplication by exponential, complex exponential in the frequency domain. And if you're multiplying by a complex exponential in time domain, it equals to what you call shifting in the frequency domain, what you call frequency shifting. Again, we will be using this in our analysis sampling. Then there's a third case. It's actually a property that we have used in the first two. It's known as the duality property. Fine. And we have actually used this duality here. As you can see, these two, they form a dual. Similarly here. Fine. Generally, how we express it is something like this, that if you have a signal x of t, you take its Fourier transform, you will have x of omega, x of j omega. Then if you have capital X of t and you take its Fourier transform, it will be equivalent to 2 pi small x minus j omega. Fine. And we will be using a specific case of this duality property which applies to the impulse. If you remember, if your impulse signal is delta t, we know its Fourier transform is 1. Fine. But if you take 1 and find its Fourier transform, it will be equivalent to 2 pi delta minus j omega. Fine. Yeah, to avoid confusion, although it is just the way you represent it, so to avoid confusion, let's simply write minus omega. Fine. Now, if you see your delta signal is something like this, it has a value here. So if this is delta omega, it is simply defined at 0, which means delta omega is the same as delta minus omega, because if you reflect this signal, it will be again the same thing. So I can say it is equivalent to 2 pi delta omega. Fine. This is a kind of it's a property. Generally, it's a duality property. It can apply to any signal x of t, and we have actually used it here. अगर आप देखेंगे, this is basically a typical case of duality property that Fourier transform follows. Fine. And if we apply it to this what you call delta signal, it is something like this. So graphically it means, let me quickly show. You have a delta signal which is a function of time, delta t. से ये आपका signal है. You do its Fourier transform. What you get in the frequency domain is something like this. It has a unit value throughout, क्योंकि one value है, flat response. Right? So this will be delta omega. Fine. Now conversely speaking, as per its dual, if we have a signal that is a DC value having a constant value, say 1 in the time domain, fine, something like this, and if we take its Fourier transform in the frequency domain, it will be a delta signal. Fine. So this is the duality property as applied to what you call delta signal. Fine. Now related to this, we have another property, that is Fourier transform. It's not a property, but it is a kind of a generalization that again we will be using in our sampling. It is a Fourier transform of a periodic signal. Normally when you have a periodic signal and you need to do its frequency analysis, you can go for Fourier series expansion. Fourier transform is defined for non-periodic signal, but we can apply Fourier transform to a periodic signal also. So we're doing a bit of analysis here. So if I have a signal x of t, it has a Fourier transform, say x omega, xj omega, it is just a representation. Fine. Then if x of t is periodic, fine, then we can also express x of t as this summation, as a Fourier series with a coefficient a of k e raised power j k omega naught t. Right. Now we just learned from the duality theorem that if I have a DC value unity, if I take its Fourier transform, it will be 2 pi delta omega. Now instead of this unity, if I have a constant value a of k, then by the linearity property, it will be equivalent to 2 pi a of k delta omega. And if I have a k e raised power j k omega naught t, then again we can use the properties of Fourier transform, and this will actually transfer into delta omega minus k omega naught. We are using this property here. This one, I am multiplying by e raised power j omega naught t, and I will have a frequency shifting by this much amount in the frequency domain. So exactly same thing. A of k, it's a constant. It had a Fourier transform of 2 pi a k delta omega. Now I am multiplying this constant by a factor e raised power j k omega naught t, which means in the frequency domain there will be a shift of by the amount k omega naught. Fine. Now this is my periodic signal. This is its Fourier series expansion. Now if I take its Fourier transform x omega, it will be summation minus infinity to plus infinity x of t e raised power minus j omega t dt. But x of t is defined here, so I will use this. So it will be k is equivalent to minus infinity plus infinity a of k e raised power j k omega naught t, then its own exponential, this thing. Fine. So next what we will do is we'll take the summation outside because it's with respect to k minus infinity plus infinity, and within the integral we will have a of k e raised power j k omega naught t into e raised power minus j omega dt. Fine. Now this integral is basically the Fourier transform of this. So we can say this is actually equivalent to k is equivalent to minus infinity to plus infinity 2 pi a k delta omega minus k omega naught. This will be x of omega. So this is basically the Fourier transform of a periodic signal. And the important point here is we have expressed the Fourier transform of a periodic signal in terms of the delta signal in the frequency domain. So it's actually shifted delta sequence in the frequency domain. Fine. This is yet another property that we will be using in our analysis. Then finally we have one more property, that is basically convolution of a function with shifted impulse. Fine. So normally our convolution operation, it is defined like this: minus infinity to plus infinity, f as a function of dummy variable tau and g t minus tau d tau. Now if one of the functions is a shifted impulse, so it's something like this: f of t, I'm convolving it with delta t minus t naught. So as per this formula, it will be minus infinity to plus infinity f of tau multiplied by delta t minus t naught minus tau. Fine. Now we have that famous relation with respect to impulse k. If you have x of t multiplied by delta say t, it is actually equivalent to x of 0 into delta t. Yeah, in general, if you have a shifted delta sequence, delta t minus t naught, this will be equivalent to x of t naught into delta t minus t naught. Fine. Because only that value will persist in x for which delta t is defined, and this is defined for t is equal to 0, and this is defined for t is equal to t naught. Defined in the sense सिर्फ इस instant पे इसका कुछ इसका unity value है. Outside this it is simply 0. Fine. So if I apply this thing here, what I will get is like this: minus infinity to plus infinity f, define it at this time instant t minus t naught, then delta will stay as it is. Fine. Now integral is with respect to d of tau, with respect to tau, so we can take this f of t minus t naught because it doesn't involve tau. We take this outside. Then inside we have the simple integral of a delta signal, which you know is always equivalent to unity. So this thing is always equivalent to 1. It is again the same thing that the total area under the under the impulse function as the time, as the width tends to 0 and height tends to infinity, it will always be unity. So this integral is equal to unity. So we have f t minus t naught. So whenever we convolve a function with the shifted impulse, we get the same function at the instant where the impulse is defined. So in this case, impulse is defined at this. So we have the function this. So these are some properties that we hadn't discussed in detail in the Fourier transform, but you will be using these properties in our description of our sampling. Okay, so we'll stop here. Next video will be using these properties to come up with some sort of analysis that will give a greater understanding of sampling in the frequency domain.